Welcome back, everyone. If you remember last time, we looked at how the brake rotors deformed when they got heated up to about 1,000 degrees. In this video, we're going to take a look at the CFD and we're going to compare the differences between a straight rotor that you see right here. This would be very common on a production type vehicle, but I just made up the design, so it is what it is. And then we're also going to take a look at what happens when you have a curved rotor. We'll look at the pros and the cons of these and which works better and why. And then once we understand that, we'll take a look at what happens when you actually spin this backwards. Sometimes they do get put on backwards by mistake, and we'll take a look at what actually happens in those scenarios. Finally, we'll look at the brake rotor when it's heated up to 1,000 degrees, like if you were on a racetrack and you had a really hard braking maneuver and then you had 5 seconds for it to cool off when you're going down a straightaway. Hopefully you find it as exciting as I do. We'll have a little fun doing this. Let's get going. Before we get going too far, I wanted to hit a few little topics, housekeeping items, if you will. First, the hub, as you can see here, I've removed the holes for the center bore and the lug nuts, obviously because they would be plugged in a real world scenario. I did forget to remove the hardware fastener holes. You'll see that a little bit in the data a little bit later, but nothing major to talk about there. As far as the setup, I established a rotating region here and I picked about 1,300 RPMs because that approximates about 100 miles per hour given most modern vehicle tire sizes. I carried over the materials from the original FEA using 6061 material for the hub and just a ductile iron for the rotor housing. And then I'm applying 1,000 degrees Fahrenheit to the outer walls of the brake rotor, so that would be where the brake pads are contacting. Aside from that, all of these simulations will be held to those same standards, and that should give us a good starting point. The first thing we're going to look at will be the velocities of the airflow going through the rotors. On the left, we can see the curved rotor, and we notice that it has a very consistent color, which indicates that the velocity is very consistent going through there. In this case, it's about 40 feet per second, versus the rotor on the right side. We can see it definitely accelerates a lot more and much higher velocities as it trends outwards on the rotor itself. And on this picture, we essentially see the same thing. Very high velocities on the straight blade rotor, extending out through the center line of that, and it seems to be in line with the previous picture. The next series of photos shows the exact same cross sections, but now we're looking at the temperature of the fluid, in this case air. On the left photo, we can see, the air coming in, ambient temperature, and getting pushed out and gradually heating up. In this case, it's exiting the rotor somewhere between 250 to 350 degrees, depending on the vein. On the right, with the fixed blade, actually put in some points where you can see the gradient of the temperature as it's heating up going outwards, heating up to a maximum temperature, in this case around 230 degrees. You do see some little artifacts around the outside of very hot temperatures. These are likely caused by some turbulence that's going on as the rotor is spinning, because it's not a perfect simulation and there's no air actually blowing around this. It's likely some of the air might just be getting trapped in there and then superheating. In the next set of pictures, we are seeing the cross section through the center line again. The curved rotor is actually on the right. I messed that up. But what we're seeing here is because it's moving substantially more airflow, and we'll get into that in a moment, that you're starting to get some of that air recycled, out through the brake rotor radially, and then back again. It's coming back through the rotor again, so it's getting heated up even a little bit more than it normally would. Obviously not a real world scenario if the car is moving, but for the conditions of this simulation, that looks like what we're seeing here. This next chart here shows each rotor with some respective data that I pulled from the simulation. On the bottom right of each graphic, you'll see a flow rate, and you can definitely tell on this one the curved rotor is moving about 50% more flow. So this is moving about 155 CFM versus the straight fixed rotor is moving just under 100 CFM. Pretty substantial improvement, which also lends it to removing more energy. The total enthalpy rate coming out of the rotor, the curved rotor, is about 20% higher than that of the fixed rotor. So we're going to see a massive increase in the cooling effect. One thing I did not anticipate was I also calculated the required torque to spin the rotor at its given RPM, and in this particular scenario, the curved rotor required about half as much torque, so you would have a lot less parasitic loss, which kind of caught me off guard. I didn't expect that, but pretty interesting nonetheless. So what are the pros and the cons of this? Well, the pros of the curved vanes are obviously the performance effects of the cooling. Hands down, you get more airflow, better cooling effect, and possibly some better performance from a parasitic drag standpoint. That just is more power, more torque at the wheels. So what are the cons? Well, the obvious is probably manufacturing, a little bit more expensive and a more complicated design. The other downside is you could put them on backwards, which brings me to my next question. So what does happen when you spin your rotors backwards? Well, obviously you get a lot less airflow, but it does still travel outwards, which semi-surprised me, but the centripetal force here seemed to outweigh the effects of the rotor trying to pull it in. The airflow in this particular case is about 30% of what it was originally flowing, and that means our total energy transfer coming out of the rotor, the heat being dissipated into the surrounding area, is about 40% of what we were seeing before. You also see a really substantial increase in the torque requirement. It's almost 3 times higher. So you will possibly see some negligible parasitic losses due to that. So this plot is kind of interesting because it shows the cross-sectional velocity of the brake rotor. And what's so fascinating about this is the velocity is considerably higher than it was when the rotor is spinning in the correct direction. There's some good reasons for that, and we'll get into it, and that allows us to really explore looking at velocity in a little bit different way. In this particular case, because it's spinning, we need to look at the velocity not necessarily in a linear aspect, but in a radial and a circumferential aspect, which will shed a little light here in a moment, as you'll see. So the question we have to ask now is, what is circumferential velocity? Well, essentially it's the velocity that it's spinning at along their circumference. The orthogonal direction, or the opposite direction of that, would be the radial direction, which will be called radial velocity. What we'll see here is that the circumferential velocity of the airflow inside of the vanes where the rotor is spinning backwards is substantially higher, essentially spinning at the RPM of the rotation, which is why it's showing such a high velocity, even though it's not going anywhere. But when we look at the radial velocity, we'll see that it's almost zero. It's becoming almost stagnant, and that's why the air isn't propagating out of the rotor, also reducing the cooling effect that you would normally otherwise see. And here's a few more pictures to drive home the point that the rotor spinning backwards reduces the airflow. You can see this is the total pressure layout here, and the high pressure region that forms around the outside of the vanes themselves, and then looking at the dynamic pressure essentially shows the same thing, that you have this high velocity moving air on the outside that's really trying to force the other air inward, while the centripetal force is trying to push it out, creating this almost stagnation in the vane itself. So now for the fun part, we get to look at what happens over a period of 5 seconds as we accelerate the velocity of the brake rotor from about 50 miles per hour to up around 100. To give a little insight into this simulation and how it was done, I set the rotor temperature I used conduction in solids, and in there you can determine the temperatures of the solids. And in this particular case, all the solids were set to a temperature of about 1,000 degrees under the initial conditions. So down here in the solid parameters, you can see I have everything set to 1000 degrees. And then our ambient temperature will be, standard conditions about 70 degrees. Like I said, this will be occurring over the course of 5 seconds. And what I've done to show the angular velocity increasing is we set a dependency condition here in the rotating region, and we essentially put in the time values that we want each RPM to occur at. So here it started off at 650 RPMs and increasing it up to 1300 RPMs at the end of the simulation. With that being said, there's no other heat sources or anything like that, so the solid bodies will just cool over time as this goes through its calculation. One thing that's kind of neat about transient analysis is we can look at predefined steps in time. So I can pull up any given time moment that I told it to save it as. In this case, I did it in about 1 second intervals, or for very specific parameters, we can actually play it through the entire plot from 0 to 5 seconds all at once. And so we'll take a look at some of that video here and see how it performs. In the first video here, we're going to take a look at the rotor, the surface of the rotor, and I actually included the mesh so you can see how the mesh sort of spins with the rest of the rotating region. I changed up the colors a little bit here to show the temperature, essentially 1000 degrees, it'll be white, and as it cools down, it'll start to turn blue. Additionally, here in the center, you will see the flow rate as it increases, as the velocity of the rotor increases as well. So let's go ahead and play this. I'm just going to put it on loop here. So we can see that the maximum temperature of the rotor drops down at right at the end of the run, about 185 degrees, but that's the maximum temperature of the rotor, so the max temp didn't drop a ton, about 15 degrees. But if we look at the minimum temperature of the surface, we're getting down into the I think it was around 870 degree range, so we're getting some pretty good cooling there. 880 I think I saw. And then here's the same sort of thing, but without the mesh this time, just so it's a little bit more clear. Here we can see a cross-section of the solid part of the rotor, showing the temperature of that solid. And one thing we can do is animate this and have it play back and forth. And this, of course, occurred at the end of the run, so this would be 5 seconds into the transient response. This will give you a little bit of an idea of how the rotor cooled, where it cooled the most, and where it didn't. You can probably hear my computer humming in the background because this is pretty graphically intensive. And then we can also hide this and take a look at the surface temperatures, which was kind of shown on the previous videos. And this is just a plot at the end of the 5 seconds of where it cooled and where it didn't. Well, I hope you enjoyed this as much as I enjoyed making it. It's been a lot of fun, and hopefully if anybody has any questions, suggestions, or things you'd like to see in the future, or where we'd like to go with this particular project, definitely let me know. Leave a comment below, give it a like, and share it if you think it's interesting. Otherwise, have a good night, and we'll talk to you later.